video we calculated the primitives of x squared and 3x by using our knowledge of differentiation. Now we can do the same thing with a number of other elementary functions. Now the first one of these is looking at the function x to the power n. Now if n is not equal to 0, then if we compute the derivative of x to the power n, where n is some fixed constant, then we get something which is equal to n times x to the power n minus 1. Now of course if we go back, then the primitive of n times x to the power n minus 1 is equal to x to the power n. So if we want to know the primitives of x to the power n minus 1, then we have to divide by 1 over n. The second function we want to consider is sine of x. If we differentiate, we get cosine of x. So if we go back, then we see that the primitive of cosine x is equal to sine of x plus an arbitrary constant. Again, if we now differentiate cosine of x, then we get minus sine of x. So if we integrate sine of x, then we get minus cosine of x. We have to cancel this minus sign. The first function that we consider is e to the power x. We know that if we differentiate, we get e to the power x back. So if we integrate e to the power x, we get e to the power x plus an arbitrary constant. And the last is the natural logarithm of x. Well, we can calculate the derivative quite easily, which is 1 over x. The same happens if we take the logarithm of the absolute value of x. So if we integrate 1 over x, then we get the natural logarithm of x in absolute value plus an arbitrary constant. So let us do a few examples. So suppose we want to calculate the integral from 0 to pi of sine of x dx. Then we look at this list, or we think a little bit. We see that the primitive is minus cosine of x evaluated between 0 and pi. So we get minus cosine of pi minus cosine of 0, which is equal to minus 1. The cosine of pi is minus 1. Cosine of 0 is 1. So we get minus 1 plus 1 is 2. Now we want to make things a little bit more complicated, and we want to calculate the primitive of the integral from 0 to pi of sinus of 3x dx. Now clearly a primitive of the sinus should be cosine, so probably it has to do with cosine of 3x. Now let us differentiate cosine of 3x. We get minus sine of 3x, and by the chain rule we get we have to multiply by the derivative of what is between brackets, which is 3x, so we get an additional factor 3. This means that if we integrate sine of 3x, we have to compensate for this factor minus 3. And so we get minus 1/3 of cosine of 3x. So what is this desired integral? It's now the value of minus 1/3 cosine of 3x evaluated between the boundaries 0 and pi. So we get minus 1/3 cosine of 3 pi, which is equal to the cosine of 1 pi, minus 1/3 cosine of 0. So we get, since the cosine of pi is -1, this thing is also -1, so we get minus 1/3 times 1, minus 1/3, so we get 2/3. So this is of course typical. If we can replace this constant 3 by an arbitrary constant a, and as a general rule we then get that the primitive of sine of a times x, where a is some constant that is not equal to 0, then we get minus 1/a cosine of ax plus a constant. And this in the same manner as we derived in the example, because if we differentiate cosine of a times x, we get minus sine of a times x multiplied by the constant a due to the chain rule, and we have to compensate both for the factor -1 and the factor a, so which we do by multiplying by -1/a. Again, if we now integrate cosine of a of x, then in a similar way we get 1/a sine of a of x. And again, by differentiating, we see that we did the right thing, and by applying the chain rule, of course, this is very important. Finally, we'll calculate the primitive of e to the power a times x. Now, of course, if we take a primitive of some function containing a term e to some power, then this primitive should contain the same term, e to the power a times x. So let us see what will happen if we differentiate e to the power a times x. Then we get e to the same power multiplied by the derivative of the power. This is the chain rule. Now the derivative of the power is a, and so we have to compensate for this extra factor a that we get when we differentiate. This we do in the same manner as before by multiplying by 1/a. Now clearly you shouldn't remember all these, or you shouldn't memorize all these primitives, you just should understand the recipe, that in fact what we do is applying a sort of anti-chain rule. We will see more general examples in the next lecture, but this is just a startup for this general anti-chain rule application.